Welcome to the lecture An Introduction to Large Deviations, and today we will discuss Sano's theorem. It is section 9 in the lecture notes. Sano's theorem. And Sano's theorem, it is the theorem about large deviation principle for the empirical distributions of independent random variables. And today we will strictly discuss a simple case when random variables take finite number of values. And then at the end of this lecture, I will formulate without a proof a general result about independent random variables with a kind of any distribution. Therefore, let me first of all make some assumptions with which we will work during this lecture. In particular, we will assume that random variables take values from some finite set, which we will denote by u. Let u, it is u1 and so on, ud, be a finite set. It doesn't matter what this set is, it could be numbers, vectors, and so on, it could be some abstract set. The important thing is that here we have a finite number of elements, and also we consider a family of independent, identically distributed random variables of a family of independent, identically distributed random variables x1, x2, and so on, taking values in U for every n. And define the random probability measure on U that is the empirical distribution of the sum of, let me write that. Let's define mu n. It is 1 over n, the sum k from 1 to n delta xk, when xk, where this delta, say a of the set A, it is a delta measure. It is defined as follows. It is 1 if A belongs to capital A and 0 otherwise for all subsets A of U. Of mu n is the distribution, is the probability measure. It is a random probability measure on the space U. In other words, so it means also, let me write that. This means that, for instance, when you integrate some function u phi of u with respect to this measure mu n du, it is the sum over n, the sum k from 1 to n phi of xk. And this mu n you can consider as a random probability measure in space of all probability distributions on U. So we will consider mu n as a random variable in a metric space, which we denote by pu of all probability distributions on U, equipped with um, the distance, with the distance so for instance, in that case, for this specific case, when U has a set of finite number of points, you can assume, for instance, total variation distance. Here it is not so important with the distance of total variation, of total variation. Sure, sure. Here, I don't want to give the general definition of the distance of total variation. I will just let's formulate the exercise where it will be more clear for you which distance we consider there, and actually you will see that this distance or convergence in this distance is equivalent to weak convergence and so on. It is the exercise 9.1 is the following exercise. Let's the first part is show that actually the total variation distance is equal to the sum. You just need to compare the measure of every atom of every point UE between two measures, and then take the absolute value. Actually, you need to consider like the vector of mass of every element of U, and then you need to compute L1 distance between them. It is exactly what is in this case the total variation distance, and having this one, therefore, for the convergence of a sequence nu n of probability measures on U to nu in that space of all measures is equivalent to convergence. That mass of every point as n goes to infinity, and that is for every I. Here also it should be I. And the second part is that nu n convergence, nu n converge in the space of in this space equipped with the total variation distance. That actually means that as we already said, that mass of every point of U converge to the corresponding mass. Then this convergence is equivalent to the convergence weakly. That means for every function, for every continuous function on U, but on U you consider the discrete topology because this space is discrete. So therefore, considering just any function for any phi, let's write like that. You have that the integral of phi d nu n converge to the integral of phi d. Actually, it is equivalent. And also the third part of this exercise is that the space here, it is, let me write that like a third part of that exercise is, I mean, this space P U is complete separable metric space. Oh, therefore, now we want to work with these measures mu n as a random element which takes values in the complete separable metric space, and we want to figure out whether we have the large deviation principle for this family mu n. But first of all, I would like to remark that we know the strong law of large numbers for independent random variables, and using the strong law of large numbers, you can show exercise 9.2. You can show that mu n, actually this empirical distribution, will converge to the distribution of the process X. Show that mu n, define it as before, converge to mu in almost surely in the space of probability measures on U when this mu is the distribution of x, for instance 1. That means this mu of every point, it is the probability that x1 is equal to ui. Right? Or if you like, you can write also that differently, or differently mu of a, it is a probability that x1 belongs to a for every a that is subset of u. That, of course, it is equivalent because here u has a finite number of elements. It is a discrete space. Good. Then we know this type. We know that roughly the strong law of large numbers for the empirical distribution. And now the question is, okay, what we can say about the large deviation principle for that family. So the goal today is to prove or obtain, maybe it's better, obtain the large deviation principle for the family mu n in the space of probability measures on U. And also find that, and also our goal is to find the rate function for this large deviation principle. And to obtain that result, I will start from the formulation of relative entropy, because you will see that at the end that the large deviation principle for that the empirical distribution satisfies the large deviation principle with rate function that is relative entropy. Then the next action is 9.1 relative entropy. And let's, for simplicity of notations, and so everything what will be here, let's assume so let first of all mu be the distribution of x1 or xn, and assume for simplicity of notations that mu of every ui is positive, is strictly positive. If it is not the case, then you can just remove from the set U that specific point, and then you can formulate first of all large deviation principle for this smaller set, and then you can easily reformulate the large deviation principle for more larger set when you obtain the large deviation principle for smaller set. It is not a problem, so therefore here we will directly assume that mu, that random variable, takes each value from the set U with positive probability. Maybe let me once again recall that it is a probability that x1 is equal to ui, and we assume that it is positive for every I. Okay, and then for some measure probability measure nu on u, on the space u, we define the relative entropy. The relative entropy, yeah, of nu given mu by h of nu given mu. It is the integral over u logarithm nu of the point u divided by mu of the point u. I mean, if you know what the Radon-Nikodym derivative is, it is exactly the Radon-Nikodym derivative of one measure with respect to another measure. And you have nu du. Or just using the fact that space u is the discrete space, it is nothing else. It is just a summation, right? By the way, if you are interested in machine learning, then there in that field this function also appear, and it has a different name. It is Kullback-Leibler distance that people actively used. Okay, we defined that function, and then also let me formulate one of the exercise. I will leave the proof of that exercise or solution of that exercise for you because it is not complicated. And actually it is some properties of the relative entropy that will be needed for us later. Exercise. One can show that or just show that h given mu, that this function as a function from the space of probability measures to R is continuous. It means that if nu n converge to nu, then the relative entropy of nu n given mu also will converge to the relative entropy of nu given mu. The second one, one can show that the relative entropy is positive if nu is not mu and it is zero when mu is equal to mu. And three is that actually this function is good. That is, the level sets of u so that h of nu given mu is less or equal than alpha is compact in p of nu for every alpha that is larger or equal than 0. And later you will see that this function, it is the right function for the corresponding large deviation principle. And we will need for this function, we will need one technical lemma about one special property of the relative entropy, which also has an independent interest. It is, let me formulate that lemma and then we will prove it. Lemma 9.4. It is that for every f, that is a function from u to r, and nu, that is a probability measure on u, one has that the integral of f of u nu du minus logarithm of integral u e to the power f of u mu du is less or equal than the relative entropy. And moreover, the equality is reached if and only if the function e to the power f of u mu of u divided by nu of u is constant on the set of all u, on the domain of all u from u, such that nu of u is finite. Because you see that here we want to divide by nu, therefore a priori it has to be larger than zero, and it must be a constant. If the function f is chosen by such a way that this is a constant, then actually here you have the equal. And it is if and only if. Let's prove that. Proof. And the proof, I would say, easily follows from the application of Jensen inequality for convex function. And we consider, instead of that inequality, we will do the following. We will consider that integral minus the relative entropy, and we will show that the difference is less or equal than this logarithm. Actually, we will move this term to the left-hand side and that term to the right-hand side. No, therefore, we start with consideration of the integral of u f of u nu du. So it is what you see here, and then we will write minus the relative entropy nu given mu, and it is equal to integral u f u nu du minus integral u logarithm of u divided by mu of u nu du. Right, so here we just use the definition of relative entropy, which is given like that. And then let's do the following trick here. Let's write this function f as logarithm of exponent of the function f of u. It is equal to the integral of u. You have logarithm exponent f of u nu du minus, and then you have integral u logarithm nu of u divided by mu of u nu du. And you see that you can put that two integrals as consider as one integral of difference of these two functions, but now you have the difference of logarithms. So you have here logarithm, there logarithm. Therefore, you can write that as one logarithm, this divided by that. It is e to the power f of u, and then you have mu of u divided by mu of u, and then you integrate with respect to d mu. And now we want to use the Jensen inequality, because the function, this logarithm, it looks like that, right? It is convex function, it is concave function. So therefore, but minus logarithm, it is convex function, and then you can apply the Jensen inequality for minus logarithm. Therefore, you will see the equality. It is less or equal than integral of u, and then you put a logarithm outside. F of u, and here mu of u divided by mu of u, and then you integrate with respect to d mu u. No, I'm sorry. It's better to write in notation here, t, right? And you have here nu du. And this is, so that and that are, so you can cancel, you will see logarithm integral u e to the power f of u new du that actually gives you what you want to see here: logarithm, then exponent of that integral. And by the way, when you apply the Jensen inequality, then in Jensen inequality, since the function logarithm is strictly concave function, you can get the equality if and only if this function is a constant function. Therefore, it is exactly the place where you have the assumption that you work with a constant, that this function, if
Excuse me.
that function is the constant if and only if you have the equality here. And
Excuse
actually,
me.
it is the end of the proof.
And how
Okay.
exactly these terms cancel out here?
You mean here, right?
Yeah.
Yes, it is a good question about that. Actually, you see, I formulated here the exercise, and I said that the function, this function nu is continuous function, right? And when you consider this part, that part here, and that part here, everything is continuous with respect to nu. So therefore, at the beginning of proof, you can assume that nu is strictly positive, I mean, for every atom, and then you see exactly the cancellation, and they will be cancellation. So therefore, here you will have the equality. So therefore, you can, to be very careful, you need to first prove this inequality for the case when the mass of every atom nu is strictly positive. So therefore, you have nice cancellations and so on, and everything works. But then when you want to prove this inequality for every nu, then you just use the approximation. Because if it happens that you start with nu where some atom is equal to zero, then you can just approximate it by that measure, by the measure with mass that is a little bit positive. And then, so therefore, and when you have this inequality for the sequence, you pass to the limit, then this inequality will be preserved.
Okay, I see. My main confusion was with yeah. So when we calculate this integral, we just get a discrete sum, and there we will have this nu of u
Mhm.
times and divided by nu of u, and
Yeah.
to cancel out. Okay, I
Yeah,
see.
yeah, yeah. But this integral actually is a summation, and therefore here you have I, and here you have I, ui, and then it will be just cancelled.
I see. Thank you.
But again, you need to be careful here because it will be cancelled in the case when nu is not zero, because if nu is zero, then you have something, because here you have zero, you actually don't have that ui, and you may not write the equality. Maximum what you have less or equal, right? In that case, it seems, yeah. But if you want to have here equality, then you want to additionally assume that this nu is strictly positive, and that by the approximation just show that for the general case. Okay, good. Thank you for your question. And then let's move further. Why we need that statement? Because later you will see when we will prove the large deviation principle, actually this term, that will appear from the Frenkel-Legendre transform, which we discussed in the Kramer theorem. And then we want to show that the supremum of that Fenhill-Legendre transform will be given by this relative entropy, and it will be exactly the place where we will apply that inequality. But it will appear soon. Okay, good. We did some preparation for the result, and now we will formulate and prove the Sanov theorem in this particular case when U is finite. It is Sanov's theorem, particular case. Theorem 9.5, it is Sanov. Let x1, x2, and so on be IID, independent, identically distributed, U-valued, random variables with distribution mu. When U is finite and mu of u is positive for every u from u. The family mu n, that is the empirical distributions of random variables delta xk, satisfies the large deviation principle in pu with rate function, that is the relative entropy. Okay, and this result will follow from the contraction principle that we discussed last time. Our idea will be the following. We already discussed it and proved in one-dimensional case the Kramer theorem, which gives us the large deviation principle for the empirical sums of independent random variables or independent random vectors. We know that that family satisfies large deviation principle. We know how to compute the rate function in that case. Now we want to build a continuous map which will map z vectors to the distribution mu n. That map is continuous, and last time we proved that the large deviation principle is preserved under continuous transformation. Therefore, using that result, we will get almost for free the large deviation principle for empirical distribution mu n. And it is exactly the main reason why here we work with the case that the state space for x is finite, because in that case this map can be easily constructed. If you are in general case, then the situation is not so nice as here, and then you need to prove that statement somehow independently and so on. So therefore here I just want to focus on this simplest case and show you what is going on there. Okay, so therefore to be able to realize this idea, we need first of all to define that random vectors which later will be transformed to the empirical distributions mu n that we consider here. Then let's start from the construction of that random variables. That is proof. And we start from so idea is actually simple how to construct here everything and how you want to identify measures with random variables or random vectors. Let me first of all let's say that the following, that our U, it is the set, for instance, d elements u1 up to ud, and then the measures, every measure mu that is okay, mu already is reserved. Let's use nu from p of u, p of that u. Actually you can write that it is written as follows. It is a sum I from 1 to d, because you have d atoms, actually you have here d elements, and every element has own mass. So mass we can denote by xi, and then we have delta ui. So actually every measure here you can write in this form, where you need to think about that measure as or what is written here as follows. You have d points. So it is u1, u2, say u3, u say d. So here I put them probably uniformly, but it doesn't matter where they are. I mean that are some points. And then mass of every point, it is x1, x2, and so on. It is xd. It is mass. Mass of point u. u1, and so on. So therefore, we want to identify, or we can identify every measure here with mass of every point. So actually our idea will be to identify that nu with the vector x1 up to xd. And now masses here. So this, at the beginning, we said that that points u, it could be anything. It must not be some elements of R. It can be taken from Rn, or even it can be some abstract objects. But now this measure here, we identify this vector, but this vector is in Rd. But also you remember that nu is a probability measure. It means that the total mass is equal to 1. So therefore these points that xi, they are not only that like some numbers, they are first of all not negative, non-negative because it is mass, and also the sum of all x is equal to 1. And then this identification, if you consider x only like that, then this identification can be done like one-to-one. If you have a measure, then of course you have the vectors in Rd which satisfy that property, and in inverse way, if you have xd satisfying this property, you will have by such a formula you can build a probability measure on u. So therefore, I hope that now it's clear for you what we want to do and what we will consider. We want to consider the space of all such x. Let's take x1 and so on xd such that, or from Rd, such that x1 plus and so on plus xd is equal to 1, and all xi are non-negative from 1 to d. And also we consider this, so this delta is a metric space, is a complete separable metric subspace space of Rg. I mean, it is trivial to check. Completeness easily follows from the fact that this set is closed in Rd, and separability. You know that if you have matrix subspace, a metric space that is a subspace of a separable metric space, then the subspace is itself separable. Therefore, the separability also is clear, but it is nice because we actually like to work discussing large deviation principle. In many cases, it is more convenient to work with complete and separable metric spaces. Okay, then having this one, let's consider also the function phi of x that is equal to the sum I from 1 to d xi delta ui. For x, that is that vector from 1 to d. And I want to note that this map is phi is continuous and bijective. The bijection follows from the discussion that we have here about this identification, but the continuity, it easily follows from the exercise which we formulated. You remember that in this exercise, we said that about the convergence, we said that this family nu n converge to nu in the space P if and only if, or is equivalent if mass of every point converges. So therefore here, if you assume that the mass of every point converge to another mass, then therefore this measure will converge, for instance, in the total variation distance to the corresponding mass. So therefore you have the continuity of one metric space to another metric space. Now let's also consider, now we want to somehow build a random variables here with values in this space by such a way that the map of these random variables will give me exactly the empirical distribution for which we want to prove the large deviation principle. So let's consider or define. And here actually idea is simple. Let's define the take psi n. It is the indicator of xn is equal to ui. I from 1 to d. Maybe in another words, it is a vector which is the following. It is x1 it is equal to u1, the second coordinate xn is equal to u2, and so on, and last coordinate it is xn is equal to ud. Let's note that psi n takes values in delta. It's trivial because every coordinate here is non-negative. But when you sum all together, what you will see, you see that actually here for every fixed omega, only one indicator is not zero, but all other indicators are equal to zero. Therefore, the sum is always also is equal to one. Therefore, indeed, for every omega, that psi n takes values in that simplex delta. And what happens if, and also let's add that psi n are independent of each other. It follows from the fact that xn are independent from each other. So then, let's say also moreover, if you consider the sum as n divided by n, that is psi 1 plus and so on plus psi n divided by n, it also belongs to delta. It is also easy to see why it is easy to see, because when you consider like the empirical sum, it is the empirical sum of every coordinate. Therefore, every coordinate in the empirical sum will be also non-negative. And when you sum all coordinates together, you see that sum of every vector is equal to 1. You sum n times 1 and then you divide by n. So therefore, you have that sum of all coordinates of the empirical sum also is equal to 1. Actually, this simplex is a convex set, so therefore, I mean this also follows from the convexity. Good. Then we have Sn. We have this empirical mean, and also remark that if you take phi of Sn divided by n, then what it is? Then it is equal to, let's compute that. It is you see we define that phi, it is a sum, then you take masses and then you multiply by delta functions. Let's write that. It is a sum I from 1 to d. Then you have the mass, but the mass of I mean that the coordinate of every coordinate of this vector, what it is the sum of coordinates of these coordinates or divided by n. So therefore it is 1 over n, the sum k from 1 to n, and then you have indicator xn is equal to ui and delta ui. But you can interchange two sums and you will see that it is a sum k from 1 to n, and then you have sum I from 1 to d, and then there is the indicator of xn is equal to ui delta ui. And now let's note that here in this sum only one term is not zero, only one indicator is not zero, only the indicator for that ue for which xn is equal to ue. But for all other e, indicator is equal to zero. So therefore here it's only the indicator is, I mean, when not zero when you have this equality, therefore this ui you can replace by xn. And then you can continue and write that it is 1 over n, k from 1 to n, it is 1, and you have delta xk. And it is exactly mu n for every n. Okay, very nice. Now we have independent vectors which takes the values in this space delta that is actually the subset of Rd. And moreover, this function phi is as gives us like of this empirical mean is that is gives mu n. Therefore, now to prove the large deviation principle, we can let's collect everything together and let's make clear what we want to do next. First of all, let's note that psi n, not I'm sorry, not psi n, but Sn divided by n satisfies the large deviation principle in Rd with rate function. That is the Fenhill-Legendre transform. Let me just write this like that. But later I will specify what this function is and so on. Now at the moment I just want to write some plan what we are going to do next. So as I said, we know we already proved that empirical sum satisfies or empirical mean, I'm sorry, satisfies the large deviation principle in RD. It is Kramer's theorem. Kramer theorem. But you see that now at the moment directly you cannot apply the large deviation, you cannot apply the contraction principle because to apply the contraction principle you need to have the function phi which is defined on this RD because you have the large deviation principle on RD. Therefore the second step will be to note or show that Sn and larger or equal than 1 satisfies the large deviation principle in delta and with rate function phi star restricted to delta because the function has to be defined on the complete space, so therefore you just do the restriction. And then the part number 3 will be show or use contraction principle because now you can use the contraction principle because you have a continuous map phi and use contraction or maybe the contraction principle to continuous map of this Sn divided by n that is equal to mu n to get LDP for mu n. And the last step, it will be compute rate function. We know the formula for the rate function in the contraction principle, but that formula is defined via infimum. So therefore, we need to compute precisely infimum and show what that rate function and find the formula for or find expression for rate function for the rate function associated with this fact. Okay, I hope that like next steps are very clear for you. And actually here we have nothing to discuss because we just need to recall the Kramer theorem and just let's step 1. Let's just note that, or maybe we'll write recall that that to write the large or to write the or formulate Kramer theorem, we need to first of all have the cumulant generating function, compute the Fenhill-Legendre transform of the cumulant generating function, and then when the cumulant generating function is finite, then we prove that the Kramer theorem and know how to and know that that this family satisfies the large deviation principle. Then step by step, let's recall that the cumulant generating function is defined as the logarithm of e to the power e lambda psi I for lambda from Rd. But now you see that this lambda, that psi I here, they are just indicators. They are vectors, random vectors, whose coordinates are either 0 or 1. Therefore, here it is the dot product. Here, this expectation z is always finite for every lambda from R. Yeah, it's trivial. Then let's define the cumulant generating function of x. It is equal to supremum, as I remember, supremum of all lambda from Rd of that of lambda x minus phi of lambda. And then by Cramer's theorem, Sn divided by n satisfies the large deviation principle in Rd with rate function that is phi star of phi star. Okay, next let's realize the second part. Namely, let's show that this family satisfies the large deviation principle on delta. We show that Sn divided by n satisfies the large deviation principle in delta with rate function phi star restricted to delta. For that, we need to consider two cases, we need to show the upper bound and lower bound. Upper bound for closed set, let f of delta be closed. But you remember that delta, it is also closed set of subset of Rd. So therefore, this implies that f is closed in Rd. So therefore, in this case, you just have the limit n goes to infinity. You have 1 over n logarithm the probability that Sn divided by n belongs to f. And since that f is closed in Rd, you can use the large deviation principle for that f. It is less or equal than minus infimum phi star and here over f, but it is the same that minus infimum or over f of phi star restricted to delta because f is a subset of delta, right? That is for the upper bound, and for the lower bound, let g delta be open. Then in this case, you can find there exists delta tilde open in Rd such that G is equal to delta intersected with G tilde. I mean, maybe it makes sense to draw here like a picture because you have like delta, it is some closed set. You can we will just sketch it, and that is delta, and your closed set, it can look as follows. And it is your end here. And of course, this set G is a closed set in delta, but G is not closed in Rd So therefore you can put like take a little bit more and then define that everything it is G tilde. And when you take G tilde now is open in RD, and when you intersect G tilde with the closed set delta, then you will get the set G itself. We need that G tilde because we need an open set in RD. We have the large deviation principle in RD. Okay, now let's write that. I'm sorry, I forgot to put here lim sup, and here has to be lim inf and goes to infinity 1 over n logarithm the probability as n divided by n belongs to G. But you remember, but it is the same as I will write at the moment this G is not open in RD, or it must not be open in RD, then let's do the following. Let's write here n to infinity 1 over n logarithm the probability Sn divided by n belongs to G intersect with delta, because you know that Sn divided by n belongs to delta also. But or maybe not. It's better to write immediately that is G tilde, right? Because if you have like random variables which take values here, and you know a priori that they are in delta, then of course this G you can replace by G tilde. The probability will not be changed. Then you have the equality, and now this set here is open, in RD. Then you can use the large deviation principle. It is larger or equal than minus infimum. And here you have phi star of x belongs to G tilde. But now you can, when you replace that G tilde by the smaller set G in the infimum, that you will get something larger, but you have minus infimum. Therefore, you get something smaller. And then I will continue larger or equal than minus infimum. And here you have x belongs to G, or just shorter G phi star. But G is a subset of delta, and it is the same if I just write phi star restricted to delta G. So therefore, you see that for every open set in delta, you got that, I'm sorry, again, I forgot to write lim inf. Then you get that this limit can be estimated from below by minus infimum over G. That exactly means that the large deviation principle is satisfied. And here I just want to say that it was a particular case when you have a particular family of random variables, a particular space, and so on. But this principle or this idea follows in any cases. If you have the large deviation principle in some big space for the family of random variables, then you can and you also know that random variables takes values in the smaller space that is a closed subspace of your bigger space. So then it doesn't matter on which space you formulate the large deviation principle, because if the large deviation principle is true for larger space, that also it will be true for smaller space. And in the inverse way, if you have the large deviation principle in smaller space and you put this, or you consider this space as a closed subspace of the larger space, then also large deviation principle is satisfied. And the reason is exactly as we showed here, because here we nowhere we use the fact that actually the delta has a specific structure or this Sn has a specific structure. Like one of the application, it could be, you remember that we formulated the large deviation principle for Brownian motion in the space of continuous functions that at 0 is equal to 0, that started from 0. We found there the large deviation principle. We proved the large deviation principle. We found the rate function and so on. But now, very easily using this idea, you can reformulate the large deviation principle for Brownian motion in the space of all continuous functions, not necessarily the function that at 0 is equal to 0. But then you will need to extend the rate function to the rate function that outside of your space, of your initial space, that function must be equal to plus infinity. Or if you go to the smaller space, then you just consider a restriction. Okay, good. We discussed it here a lot, and now we finish it with the discussion of the second part. Now we need to go to the third part, and we want to apply the contraction principle. And actually, here is nothing to discuss because it is just the direct application. Let's note, or let's by so it is part 3 by the contraction principle. It was theorem 8.1 in lecture notes, the family mu n, that is phi of 1 over n Sn, satisfies the large deviation principle in the space Pu with rate function. Let me write I mu that is equal to infimum over all rate function, that is phi star of x, such that phi of x is equal to nu, or x from delta, right? Yeah, and here nu is from pu. Right, it is what we did, how we formulated that the rate function, it is just the infimum of all rate function over the pre-image, right? Here is nu, so you compute the infimum over all x such that phi of x is equal to nu. Here we also specified that x are taken from delta. Let's remark that phi is bijective. Bijective map. Therefore, when nu is fixed, that we know what x is, right? Then this x is equal to, for instance, zx here, it is phi minus 1 of nu, and this is what, if you have mass, if you go back to that picture which we had here about this identification, you see nu is identified with masses. Therefore, the pre-image, you define the map which acts in this direction, but now when you want to go in this direction, what you need to take? You just need to put here the masses of every point of your space. Therefore, this is the vector which has the component nu of u1 and so on, nu of ut. This the vector, and then the rate function, it is just the phi star of the point of nu ui. I mean of that vector, right? Let's maybe write that like that. I will just take this vector and we'll copy it and we'll put it here. That vector. It seems that we need to close one more bracket. For every nu from the space of probability measures on U. So therefore, everything now what you need to do. So our for goal, like for, we will show that I of nu is exactly the relative entropy given mu. So it is the question that actually this function that is phi star of this is defined as the relative entropy. And for that, we need to make some computations. We need to first of all compute the Fenhill, compute the Combline generating function. After that, take the Fenhill Legendre transform and see that that exactly gives us in that points. It gives exactly the relative entropy. Okay, yeah, then compute phi of lambda. Let's take lambda, it is lambda 1, and so on up to lambda d, and then you know that this, it is logarithm, it is the expectation of e to the power, and you have the inner product, lambda with xi, right? But with, say, with xi1, but now let's write this inner product. We know precisely what the, how xi is defined. It is indicators to d, and then you have lambda I, and you have indicators. X1 is equal to ui, and it is equal to the logarithm. And here, actually, here everything is looks very nice because you see that this sum here, in this sum, only one term is not zero. And for every fixed omega, only one term is not zero, and all other terms are equal to zero. Let's assume that only that lambda I is not zero. Therefore, what you will see? You will see e to the power lambda I, but for which I? For that I for which x1 is equal to ui. Therefore, that exponent can be written as e to the power lambda. You can put here the sum from 1 to d, and then you can write e to the power lambda I and put indicators there. It is indeed a very convenient trick that follows from the fact that in this sum only one term is not zero and all other terms are zero, and only the term which satisfies that property. Therefore, it is the same whether you have summation here or you have summation outside the exponent. Two results are the same because here also you have only one term which is not zero. But this is much easier to compute because you have what? You have expectation of sum, and you can move this expectation inside. You see that it is logarithm the sum I from 1 to d e to the power lambda I, and then the expectation of indicator, it is a probability. But this probability, it is mu, e to the power lambda I mu of ui. Or if you like more, you can write that. Okay, at the moment, let's leave this like that, and then we will continue. Um, or maybe no. Let's write this as an integral because now you can define the integral. This as an integral, you can write that as a logarithm of integral over u, and then you have e to the power f. I will write lambda of u, and then you have mu du, where this function f lambda of u is defined as follows. It is lambda I for u is equal to ui. I mean, or in different ways, you define this function is defined as follows. On every ui, it is lambda I. Therefore, the integral, you remember that integral, it is the summation over all atoms. When you sum over all atoms, you multiply by a measure of every atom, and then you have e to the power function, but the function on every ui, it is equal to lambda I. So therefore, you can write that as an logarithm of integral, and actually it is one of the integrals that you saw in the properties of relative entropy. Thus, you have that I of nu. It is a Fenhill-Legendre transform. It is phi. I'm sorry. It is phi star of the vector nu of u I I from 1 to d, and it is equal supremum over all lambda from Rd, and then here is the sum I from 1 to, we just write the Fenhill-Legendre transform that this supremum, you see, we wrote the Fenhill-Legendre transform somewhere here. You see that Fenhill-Legendre transform is supremum, then you have lambda multiplied by x, and then you have phi of lambda. Then we do exactly that. It is lambda I. And then you have xi, but your xi, it is nu of ui minus phi of lambda. And let's continue. It is a supremum. Lambda belongs to Rd of integral of the function f of lambda, the function of which on ui takes values lambda I, of u nu du. And then minus the function lambda, which is computed here. It is logarithm. Logarithm of integral over u e f lambda of u mu du. And then let's consider what it is here. It is integral of f with respect to nu, and then the minus logarithm integral of exponent mu. Let's go to the beginning of this lecture and see here. It is integral of f nu minus logarithm. And we showed that for every function, it is less or equal than the function h. And moreover, you can find a function. So if you choose a function such that this is constant, then you moreover has the equality. But let's go back. Here you have supremum, then from one side it is less or equal than h of nu comma mu, but you take supremum over all possible lambdas, or it is equivalent over all possible functions on u, and therefore you can find some lambda such that actually this is equal to exactly. Then you have the equality. And it finishes the proof of Sanov theorem. Okay, and the fact that h is good rate function, it follows from the exercise, because you see that that also here in the space we said that with satisfies with rate function. It's better to write here with good rate function. Okay, with good rate function. H of mu is completely then the proof of this theorem is finished. And you see that our final result actually doesn't depend so much on the fact, I mean, at least the formulation of the result does not depend on the fact whether this u is finite or infinite. If you can introduce the relative entropy by the reasonable way on that space u, that is an arbitrary space, then there is a big hope then also the Sanov theorem is also true. And it is exactly the case. Well, then let me formulate the Sanov theorem in general case. Sanov, it is 9.3. Sanov theorem, general case. You remember that working with space U that was discrete, we didn't pay so much attention on what the topology is there, but because when you work with discrete space, you always consider the pointwise topology, like the discrete topology. But now we want to consider U that is arbitrary space. And when you can work with probability measures, it also it's good to have some topology on the space on which you define probability measures. Therefore, we will assume that U is a complete separable metric space. Now, let U be a complete separable metric space. Let me recall that before U was U1 up to UD. And the matrix there, it was discrete matrix. Discrete metric, it means that if two elements are different, that the distance is equal to 1, but if they are the same, that the distance is equal to 0. Then we also consider PU that is equipped, maybe short. Consider the space of all probability measures, the space, maybe here we will put PU of all probability measures on U equipped with the with the topology of weak convergence with sorry with the topology of weak convergence. That means that nu n converge to nu in P of U if for every phi belongs that is continuous bounded function on U, one has that the integral of phi d nu and converge to integral phi d nu. It is, I believe that you are familiar with that topology, that you are familiar with convergence in that topology and so on. And in particular, you know that if space U is complete separable, then the weak convergence is metrizable. So actually, one can define the metric on the space PU, and this space will be a complete separable metric space. One can show that. This space is complete and separable metric space. More precisely, one can introduce some metric on this space such that the convergence in that metric is coincide with weak convergence, and the space with respect to that metric is complete and separable metric space. Then we want to introduce to introduce the concept or the definition of relative entropy. And here the idea is the following: we just defined the relative entropy no entropy h nu given mu by h nu given mu, it is equal to, as before, it has to be the integral of u, but now it has to be the derivative of d nu d mu of u, nu du. But of course, the derivative exists when mu is absolutely continuous with respect to mu, and plus infinity otherwise. So here it means that nu is absolutely continuous with respect to mu. It means that if mu of a is equal to 0, then implies the nu of a is equal to 0. And you know that Radon-Nikodym theorem gives us that exists the density of nu with respect to mu denoted by d nu d mu. that is integrable, a non-negative function, and I believe that you know what means that some function is a density of one measure with respect to another measure. So therefore, you just take the density, you put it in a logarithm. That object is well defined because, okay, it can happen that somewhere the density is equal to 0. But if the density is equal to 0, then also that measure is equal to 0. Therefore, and you don't actually integrate with respect to that points which are equal to 0. So therefore, this actually object is well defined object. Also, you can prove that this function is non-negative, and it can be, and that is needed for the rate function because you know that the rate function is non-negative. And in that case, the Sanov theorem is formulated as follows. It is theorem 9.8. It is Sanov. It says that let x1, x2, and so on be IID random variables taking values in U. Or let's say random variables on U, maybe in U. With distribution mu. When U is a complete separable metric space. And of course, mu is an element of P of U. Let define the empirical distributions delta xk n larger or equal than 1. Then the family mu n satisfies the large deviation principle in PU with a good rate function that is the relative entropy. Okay, unfortunately, we have no possibility here to discuss the proof in the general result. We discussed the proof in a particular result, and you see how nicely it follows from the contraction principle. Here, you need to be one needs to work more harder to obtain the large deviation principle. But at least I hope that after you saw that particular result, it is not complicated to believe that the result of this theorem is correct. If you want to see the proof, I leave in lecture notes some references. For instance, a reference to the book of Dembo and Zaiteuni, and you can find this very nice book about large deviation principle, and you can find the proof of this theorem there. Okay, and actually it is everything what I wanted to discuss with you today. Next time, let me check, we will discuss the Vardan's lemma and also the Brooks theorem. We will discuss what it is next time on Friday. Then after that, there will be one more topic about the exponential tightness and then some application. So actually, I plan that we will have three more lectures. Okay, and for today, it is everything. Then thank you so much for your attention.